And then from here, it is not very obvious that the 10 kilonewton is the axial load, is it? Is it the 10 or the 100? The 100 kilonewton, oh, my eyes are so bad. It's not clear. Right? If you look at this view, it's not clear that the 100 kilonewton is actually the axial load. But if you look at the previous view, if you view it 2D, you're going to see that. Or not. Okay. Now, so from here, we know that we have a moment in the x direction. Okay. So now we like to compute moment. So I'm just going to declare going in this direction. Okay, is my moment in my x direction. Okay, moment in my x direction. Now, the positive rotation and negative rotation that come. Okay. I decided to call clockwise to positive. Okay. Now, from here, again, the rules that I told you is what? When the force, let's look at the 100 kilonewton. When the force is what? Parallel to the what? To the centroid, what do you use? You use this distance over here. Are we clear? Right? For the 100 kilonewton. When the force is parallel to the centroid axis of interest, the perpendicular distance is to the centroid. If now we look at the 25 kilonewton now, the 25 kilonewton is perpendicular to the centroid of interest. So if I were to project here, right, this is what? Perpendicular. When that's the case, we take the distance now is between here to here. It is towards the what? Towards the element. Okay. So from here, we know that this is equal to 0.5. Okay. And then in the other view, we need to somehow find this distance over here. Okay. We don't know this distance. And this we can acquire from the table. Okay. So when we acquire from the table, over here, we need to find what is our D. So the one that we are going to use, I'm going to highlight it. Okay, the one we're going to use is this one. Okay, undo one again. We are going to use this. Okay, I'm sorry. The one that we're going to use is this data over here. Okay, so we know we want to find the distance from where? From here to here. And this distance is D divided by 2. Okay. So in D divided by 2 is 205, right? You can see that this is 205. So that distance over there is equal to what? It's equal to 0.205 divided by what? Divided by 2. Okay. So we know that this is equal to 0.205 divided by what? Divided by 2. Okay. So the 25 is positive, and the and the perpendicular distance is 0.5. Okay. The 100 is also generating a clockwise moment, plus 100 times 10 to the power 3 multiplied by 0.205 divided by 2. So this will come out to be 25 power 3 times by 0.5, 12500, plus 100 power 3 times by 0.205 divided by 2, 10250. So this will be equal to 12500 plus by 10250 is equal to 22750. So it's 22.75 times 10 to the power 3 Newton meter. Okay. And we are aware, we have the confidence to say that the moment now over here, right? So over here, we have moment in your what? Moment in your X, right? And over here, this is compression. And on this side, this is tensile. So from here, we know that the formula we're going to use is stress Z is equal to mx over I multiplied by Y. And we are aware that for element A, is it tensile or compression? Can you tell me, please? Tensile. And element B, it is what? Equal to what? 0. Because it's exactly as aware. Once you got this analysis done, the rest is just putting in what? Okay, the rest is just putting in numbers. Okay. Now, let's look at the formula now. Okay. Now we finish analyzing, and there's one more detail that we have to be very careful about. Okay. So next we're going to put in numbers. The formula that we're going to use is stress Z is equal to PZ over A plus minus mx over Ixx multiplied by Y plus minus my over Iyy multiplied by x. Okay. So now I'm going to take the cross-sectional view again. Okay. Right. Okay. We need to know what is our area first. Let me start on a new page, okay? So it'll be easier for you and me. So from here, all right, we have to find what is our Ixx. So our Ixx from the table, I'm going to copy the whole table. All right, and I'm going to copy this diagram. Right. So now you find the convenience of making sure that the transformation on the question and the transformation on the data handbook, the one on the right is from the data handbook that's related to the table here, are in the same orientation. Then you will not be lost. Yes. You're not considering the XY plane because it's not contributing to the normal square. Okay. Now listen. What I'm teaching you guys, we are just halfway. Okay? To really do this in detail, what did I not consider? Shearing strength. Okay? We have not considered what? This is just half. So we cannot actually design yet. To design this, what do you need? So you know how to break down the external and moment. You have not considered the shear force yet. Okay, which we will do after term test 2. Okay. Then we now have you learned Mohs circle? You have learned Mohs circle. Okay. So we are halfway. Okay, not really there yet, but halfway yet. Okay. So for this case, what we have now is we know our Ixx value is equal to 40.1, 40.8 times 10 to power minus 6 meter to power 4. Okay. And then our Iyy is equal to what? Iyy is 9.03. 9.03 times 10 to the power minus 6 meter 4. And our cross-sectional area is equal to what? 5320 times 10 to the power minus 6 meter squared. Okay. So what do we have now? We have this. We are good to go. 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 The next part where a lot of students make mistake are this distance. You have to be really, really careful regarding the magnitude of this distance. Okay. Now, if we look, let's focus on element A. Okay, let's focus on element A. Okay, so element A, right? For element A, the x is equal to what? So the x is the horizon is so this is our x distance, and over here this is our y. So for element A, the x value is what? Okay, so we need to have BF, which is 0.166 divided by 2 minus by 0.075. Okay, so from here for element A, right, this will be equal to what? 0. So there is our BF, 0.166 divided by 2. So the answer is 8 times 10 to the power minus 3 meter. Okay. Likewise, we do y. Y is the vertical distance. So at element A, it's exactly at the edge over here. So it's equal to d divided by 2. So d is equal to 0.205. So it's equal to 102.5 times 10 to minus 3 meter. Are we clear? So the next thing that we're going to look for, we are going to look at element B. Okay. So element B, the x is equal to what? So element B, the x is, so we are going to take TW, okay, 724 times 10 to the power minus 3 divided by 2. Okay, so 7.24 is equal to 3.62 times 10 to the power minus 3 meters. And then we are going to look in the y distance. So the y distance is exactly on the centroid is equal to 0 meters. Okay. Once you got this, okay, once you are very confident about this, if this question is for 10 marks, 10 marks is in your pocket. Okay, 10 marks is in your pocket. Okay. So now we are going to deal with element A. Okay. So we know that stress Z for element A will equal to, so the PZ, okay, so the PZ is equal to minus 100 times 10 to the power 3 divided by the cross-sectional area, which is 5320 times 10 to the power minus 6. Okay. So the next thing that we're going to consider, we are going to consider moment about y over Iyy multiplied by x. Okay. So let's put in the numbers first. So moment about y we calculated is equal to what? Moment about y. 9600. Okay. So we know that this is 9600 divided by Iyy 9.03. So element A, the x distance is 8 times 10 to the power minus. Okay. So if we go back to the previous graph or previous page, right? Moment about y, right? Moment about y is going to generate a what? A compression on element